All right, let's dive in to one of the most powerful and maybe one of the most intimidating sounding concepts in Swift, polymorphism. I know it sounds like a big, scary word, but I promise by the end of this, you're going to see how this one idea can make your code so much more flexible and clean. So I want you to start by just thinking about this question right here. What if a single name, a single command, could actually act differently depending on the situation? That's really the core idea we're going to unpack together.
And that idea, well, that's what we call polymorphism. It literally means many forms. In programming, it's this amazing ability to have a single interface, like a function name, that can handle all sorts of different data or behaviors. And why do we care? Because the goal is to write code that's truly adaptable and that we can reuse all over the place.
Okay, so how does Swift actually pull this off? How does it make this many forms idea a reality? Well, it basically uses two key techniques. We're going to explore both, and we'll start with the decisions that are made before your code even starts to run. First up is what we call compile-time polymorphism, or as you'll probably hear it more often, method overloading. You can think of this as the predictable, pre-planned version of polymorphism. The compiler figures everything out just by looking at your code way before your app even launches. And at its heart, the idea is actually super simple. Look at this. Both functions are named add, the exact same name. But what's different is their signature. A function signature isn't just its name, it's the name plus the types of parameters it takes. And here, one is built for integers and the other one is for doubles. That little difference, it's everything. And here's what that looks like in some real code. Inside this one class, math operations, we have two functions, both called add. And Swift is totally cool at this. It doesn't get confused because it can easily tell them apart based on the kind of data you give them. So when we actually go to call the add function and we hand it to integers like 5 and 3, the Swift compiler knows immediately what to do. It looks at that and says, ah, you mean the integer version of add. It makes that decision right then and there. And of course, you get the result 8. And you guessed it. If we do the same thing, but we use two doubles, like 2.5 and 3.5, the compiler again just matches the input to the correct function signature, it picks the double version, and we get 6.0. And that's it. That's overloading in a nutshell. One name, multiple different signatures, and the decision is made at compile time. Okay, so that was the pre-planned stuff. Let's move on and see how this idea can get even more dynamic. Now we're talking about runtime polymorphism or method overriding. This is where things get really, really cool, because the decision on which method to run happens while your program is actually running. Now, this form of polymorphism relies entirely on inheritance. So just imagine a simple family tree. At the very top, we have a general animal class. Then, underneath it, we have more specific types, our subclasses like dog and cat. They both inherit from animals, so they are animals, but they're also their own distinct things. And here's the code that makes it all happen. Our base animal class has a function called sound. Now both dog and cat get this function because they inherit it, but they use that super important override keyword to provide their own unique implementation. The dog is going to bark and the cat is going to meow. Okay, this is where the magic really happens. We can create a single array of type animal, but then we can put different kinds of animals into it. We can drop in a dog object and a cat object. We're treating them all as if they're the same base type. So the big question is, what happens when we loop through and call the exact same animal.sound method on each one? For the very first item in that array, the program checks its actual type at runtime. It sees, hey, this thing is actually a dog object. So it executes the dog's overridden sound method. And what do we get? Bark. Then the loop moves to the next item. The exact same line of code, animal.sound, runs again. But this time, the program sees the object is a cat. So it dynamically calls the cat's version of the sound method. And the output is meow. One line of code, two completely different behaviors, all decided on the fly. That is the incredible power of overriding. So we've seen the how, but it's just as important, if not more important, to understand the why. You know, why should you go through the trouble of using polymorphism in your projects? What's the real payoff here? Well, the benefits are just huge. It leads to way cleaner designs. Think about our animal example. We wrote that loop one time, and now it works for dogs, cats, and any future animal subclass we might create, maybe a lion or a duck.
That slashes code duplication and makes our whole system incredibly easy to extend. This dynamic behavior is the secret to building software that can grow and change without falling apart.
And hey, this isn't just some abstract theory. As the source material points out, this stuff is fundamental. If you're learning Swift or getting ready for a technical interview, you absolutely have to know polymorphism inside and out. It's truly one of the main pillars of object-oriented programming. So, at the end of the day, we've seen that polymorphism is really a tool for creating flexibility. It's what allows our code to take on many forms, to adapt to new things we throw at it, and to grow without becoming this tangled, unmanageable mess. So, the question I'm going to leave you with is this. Now that you have this powerful tool in your belt, how are you going to use it to make your own code adopt and grow?